So how do we think about spontaneity as it relates to these two energy parameters that we've talked so much about, which are enthalpy and entropy, specifically the changes in the initial and the final state, the reactants and products. And earlier we talked about the example of liquid water spontaneously turning into water vapor slowly, but this happens if you say leave a glass of water on your table for several days. And we said, well, it has to take energy from the universe to do this because it needs to break those intermolecular forces holding the water molecules together, those hydrogen bonds, in the glass of water. So it's getting heat from the universe and it's driving that process. We also mentioned that it is increasing its entropy because it's going from a liquid state, which has some order, to a gaseous state, which has much less order. And the system is spontaneous. But in contrast, we had this thermite reaction that I described, which has an enormously negative delta H, meaning tons of heat is released from the system, but it also has a positive delta S, small but positive. This is also spontaneous. So what does a non-spontaneous system look like, and how can we understand how the magnitudes of these two values predict the spontaneity of a chemical reaction? So we need a new type of energy to define that really is the energy that defines whether or not a system is spontaneous or not. And we call that Gibbs free energy. And this is one of the most important expressions in all of chemistry because it accounts for both the enthalpy changes, the heat changes in a system, and the entropy changes. And those taken together give an overall free energy change. And it's this change that dictates whether or not a system will be spontaneous. So before we had only been thinking about enthalpy or entropy, but we hadn't thought about what do they do, how do they operate together, and how do we account for them together. And it's a really simple expression where you're really just taking both of these things, but you're sort of modulating S here, the entropy, by temperature, and that's simply because temperature highly impacts the disorderedness of a system. And the conditions for spontaneity with delta G are really simple. And this could be thought of graphically, because for me that's almost more important to think about. But if we have G on our y-axis and reaction progress on our x-axis, just like normal, now we have our reactants and our products, and G here is a function of both H and S, rather than just enthalpy or just entropy. And now, anytime there's a decrease in G from reactants to products, which would be marked sort of graphically like we have here, then we'd consider that system spontaneous because there's an overall decrease in energy of the system, accounting for both types of energy in this case. If G is the change in free energy is 0, then it means our system is at equilibrium. And what does that mean? Well, that just means that there's no energy difference now, or at least no free energy difference between reactants and products. So there's equal driving force in both directions. Doesn't mean it's not reacting, because remember what equilibrium is, it's a dynamic process, but there's no change in the concentrations in reactant and product, which means there's no overall change in the energy of reactant and product. They're both at the same energy, so there's no push in either direction in a macroscopic state. And then that final example is when G, or the change in free energy, is greater than 0, then that's that uphill example where we have a reactant down here and a product up here, and the overall change requires energy from the universe. This is a non-spontaneous process. But it's important to know here that there's a variety of combinations of signs, positive, negative, for the change in enthalpy or the change in S that can produce each of these conditions. So in the previous example, we talked about two different situations, one where both of these were positive and one where one was negative and one was positive. So it's important that you are able to understand intuitively that both of those can still yield a negative value of delta G, simply because this term can be weighted by T. So when T is really large, then this whole term becomes large and negative. And when this T is very small, then the whole term is very small. And so there are lots of condition states, or even different temperatures, where a system can convert from a negative delta G to a positive delta G, which tells us that temperature plays a huge part in spontaneity. So let's look at an example. So this is the reduction of rust, iron oxide, to pure iron. So this is a nice industrial process where you could take a rusty bike, a rusty car, put it in with pure hydrogen gas in a sealed chamber, and think about converting it back to pure iron with some water vapor. So we want to evaluate, is this spontaneous, using our new expression, which relates delta S and delta H to this new term delta G, when the system is at 25C and we have tabulated versions of delta H and delta S. To be honest, or just to be clear here though, you should have the capacity to either find these on your own for the whole reaction, which are given to you, or generate them from their individual values, because we know how to do both of those. We used to do that in thermochemistry for delta H, and we just in a previous video walked through how to do that for the standard molar entropies. So in this case it's pretty simple because I'm giving you all these values, but I won't always do that because you know how to find these on your own, and I'm just popping them into this new expression. The place that's a little bit tricky if you're not really careful, and why you should always include explicit units, is that notice how the energy change for delta H is given in kilojoules, that's thousands of joules, and delta S is in joules per Kelvin. And so if I need these units to work out, then I need to either work in joules or kilojoules. And so I just chose to work in joules for delta H. And so you can see instead of 98.8, I have 98.8 times 10 to the third joules, because these are thousands of joules. And then minus, and be careful about temperature as well, because we're working in units Kelvin for temperature here. And so I needed to convert my 25C to 298.15 Kelvin, and then I'm able to have these units go away nicely. And so now if I look at my units, I'm adding joules to joules, which is what you want, which means our answer here in the end will also be. And that adds up to something like this, 5.66 times 10 to the 4 joules. That's a positive value. And so that means delta G is positive. So when you're confused, just sketch that out. What does that look like? If delta G is positive, that means the reactants are lower in energy than the products, right? You are going uphill in this system, so a positive delta G means that this is a non-spontaneous reaction at this temperature. We would not expect it to occur at this temperature and under standard conditions, which is denoted by the degree symbol. Let's take this one step further. We know that under these conditions it's not spontaneous, but could we figure out a temperature where that delta G transitions from positive to negative? Well, sure. That would be occurring when delta G is 0, right? That's the transition point between positive and negative. So could we set this whole thing to 0 and solve for T? Yeah, of course we can. So I just did some simple algebra. I set this expression to 0, rearranged it, solved for T. So temperature is when delta H is divided by entropy change here. It's important to know that what is the condition when delta G equals 0? Well, that's equilibrium, right? So this is the equilibrium condition. So we would have no difference in free energy for reactants and products when the temperature is equal to 698 K. And so if we were to increase or decrease the temperature here, delta H and delta S are assumed to be intolerant to, or not sensitive to T. That's not totally true, but in this class we're going to assume that. And so that really just means that by raising and lowering T, we can modulate whether or not the system proceeds in the forward direction or the reverse direction. Because remember, when confused, draw it up, we are at a system condition where the reactants in the products are exactly equal to each other when this thing is at 698 K. That's what equilibrium means. If I decided to increase K or T to above 698 K, what does that change? Well, I go back to my expression here, delta G equals delta H minus T delta S. That means I'm increasing this value, which means that I'm increasing the overall negative quantity here, which means that this system becomes more negative. So what happens to the picture here? Well, that thing becomes negative. So what we're really doing is changing where we are in this equilibrium space, where now the reactant is above the product and there's a negative delta G. Similarly, let's say that's when I'm increasing temperature. Oops. So I could do a similar example. We'll do that in sort of this red color. If I decrease it, what am I doing? Well, I'm effectively decreasing the energy of the reactant relative to the product, and now I'm in a position where it's an uphill battle, where it's no longer spontaneous. And so that's all that's being modulated here, is these two terms relative to each other by T, which is something we can control. This is really useful if you're a chemist, right? Because now you can look at a reaction that you want to run and you can understand what temperature should be required for you to get the system to become a spontaneous one that's going to happen without any energy input.